the very last thing we're going to talk about from Chapter 2. These are notes. And we're going to talk about calculating error. So it's the last slide we haven't talked about. You have actually already done this. We just called it percent loss. It's the same thing. Percent error is, in essence, percent loss. And it's the difference between the accepted and the experimental value divided by the accepted value times 100. The accepted value is whatever's true and correct when we're talking about error. When we were talking about loss, here we were using the total sample to start with minus what you recovered divided by the total sample. It's the same concept. And just like with loss, you can have a positive or a negative error. If you have a positive error, your accepted value is greater than your experimental. If we're thinking about this in terms of loss, what that means is you had some loss. You started out with more sample than you recovered. If you have a negative percent error, your accepted value is less than your experimental. It means that you magically made matter materialize. You probably masked something when it was wet. So we very often do these problems in regards to like calculating densities. We'll do percent error on calculating density. So I'll give you an example. Density equals mass per unit volume. You all know that. As a matter of fact, you recently attempted to find the density of some unknown liquids in a lab. So let's say that you're doing a control and you're measuring the density of water. Now here's what we know. Water is used as sort of an assigned point. Water has a density of 1 gram per 1 milliliter, so it has a density of 1.0 grams per milliliter or grams per cubic centimeter. Well, let's say that when you measure your sample on your balance with your graduated cylinder, you're getting a mass, so you're getting a volume, you are reading 100.0 milliliters of water, but you're getting a mass of 100.030 grams. I could ask you a question like this. What's your percent error? Well, what steps do you have to take first to solve this problem? So first you have to find your measured density of water. So we've got our 100.030 grams divided by 100.0 milliliters gives us, so I get a raw answer of 1.003 grams per milliliter. Let me ask you this question. How many sig figs can I have in my final answer? Look at my givens, my measurements. How many? 4. I can have 4 sig figs. This is what's limiting me. This has got 1, 2, 3, 4, 5, 6 sig figs. This has only got 4. I can have 4 sig figs. What's my final answer? Recorded answer. How do I take this down to 4 sig figs? 1, 2, 3, 4. 1.000 grams per milliliter. What's my percent error? You can do this without writing anything down. What's my percent error? It's 0. We're perfect. Are we really? No, but the sig figs sure make us look good here, don't they? Okay, let's examine this. So to find our percent error, I'm just going to abbreviate it that way. We take accepted minus experimental divided by accepted times 100. Well, what did we say the accepted sort of official density of water was? 1.0 grams per milliliter. So our percent error is 1.0 grams per milliliter minus our experimental value. That's what you calculated based on your measurements, 1.000 grams per milliliter, divided by 1.00, or no, just 1.0 grams per milliliter. Okay, what do we get? We have 0% error. Oh wait, does that come out to 100% error? It's not, it's 0% error. Once you get a 0 in there, it's 0. 1 minus 1 divided by 1, 0. At that point, we don't multiply by 100 anymore. 0% error, we're perfect. Now, were our measurements really perfect? No. Let's do one where we have slightly more realistic measurements. I would be shocked if you got a measurement this awesome with high school grade equipment. You probably wouldn't. So you've re-measured water, you and your lab group, and this time you measured that same 100 milliliters. You got 98.701 grams as its mass. What is its density? Grams divided by 100.0 milliliters. So I have a raw answer of 0.98701 grams per milliliter. Is that what you have? I would imagine. It's fairly simple arithmetic. Okay, but that's not really what we were after. What we were after is the percent error. So percent error is equal to the accepted value minus your experimental value divided by the accepted value times 100 to express it as a percentage. So the accepted value we said is 1.0 grams per milliliter minus our 0.98. Oh, what's our final answer for density? How many sig figs are we allowed to have? Fingers. 1, 3, 5, 0, 4. 4. Because we're looking at this. 1, 2, 3, 4. That's our limiting factor. So 1, 2, 3, 4. Our final answer is going to be 9870 grams per milliliter. That 0 is significant. Okay. 0.9870 grams per milliliter divided by 1.0 grams per milliliter times 100. What is our percent error? Anybody else got something that looks a lot like that? No? Did I screw up? Hold on. Let's go back to before Moser screwed that up. Woo! That was a sidetrack. Okay, so our answer then is what? 1.3. Whoops. Okay, give it to me again. Just 1.3? Okay, now let me ask you this. This is perfect. What should it be? Is that the correct recorded value? Why not? You're shaking your head, Wyatt. Why not? Should have zeros, because how many sig figs should we have here? 4, because that shows us our level of precision. So to get 4 sig figs out of 1.3, what do you got to do? Yep, 1.300% error. And frankly, that's pretty darn good. Being down in the 1 or 2% error is really quite good. That shows a high level of precision. Okay, here's what I'm going to do. I'm going to add some problems. Do you want to do any more that are percent error together? I think you got this. Yes, ma'am. We have 4 sig figs because we have to go all the way back to our measurements. So when you're doing sig figs, that's a great question. you always look all the way back to your givens. If those givens are measurements that you took, you look all the way back to your original measurements. If they're measurements that were given to you in a problem or numbers that were given to you in a problem, you look back to the original givens. Conversion factors do not count against you. So like our value of water is a sort of a known quantity. It's assumed to sort of have infinite sig figs. We are basing our sig figs on our givens and our own measurements, but you have to go all the way back to the beginning, and any number that went into your problem that was a given or you measured it, that counts for your sig figs. Okay? Do you want to do one more that's a negative % error, or are you good and you just want to work on practice to get practice on your own? Okay. Hands, show of hands. Practice on your own. One more. Okay, I got a few who want one more. We'll do one more. So if you're going to look at the boiling point of ethanol, ethanol is alcohol. You would take a sample of ethanol, you would heat it with a thermometer in it until it all vaporized. And during the entire period where it is vaporizing, you're going to have one temperature reading. It's going to stay at that temperature until all the particles have escaped into the vapor phase, and the temperature is going to shoot up. Well, the fact is, you can measure that. You can do that in a lab setting. So we have a known value for the boiling point of ethanol, but let's say you measure it and you get 57.2 degrees Celsius for the experimental boiling point of ethanol. Okay. Now, the generally accepted value, and I'm quoting this off the top of my head, I believe it's 56.0 degrees Celsius, as I recall. Now, the quality of the thermometers that we have in this room, they don't have, their markings are in degrees, individual degrees. They don't even have tenths of a degree marking. So the fact that you're measuring this at 0.2, you're really eyeballing that. And, you know, is there some fudge factor? Yeah. Does it depend on how your eye is aligned when you read it? Yeah. Is there a lot of room for error? Yeah. So this is not terrible. Let's look at what your % error is on the boiling point of ethanol. Well, 56.0 minus 57.2 degrees Celsius divided by 56.0 degrees Celsius, whole mess times 100. Okay, so we get negative 1.2 divided by 56.0 times 100. Okay, there's my raw answer. Valentine's Day. Oops. Oh, sorry. 2.142857143% error. Negative 2.14. How many sig figs can I have? Fingers. Wow, I see 2, 3, and 4. And I see people fudging. Oh. 3. Why? Where am I getting the 3? From my measurements. My measurements. The given values. Those accepted values don't count for or against you. My values. So that would be negative 2.14% error. Which is, you know, not at all terrible for the kind of quality of instruments that you're dealing with for temperature calibration. Okay, assign some extra practice problems, and then you're on your own.